Okay. So, next is loss of branch 2, branch 2, right. So, similarly P loss 2 will be R 2 into P 3 square plus Q 3 square upon V 3 square. This already I have told you, right, that I mean if you just if that electrical equivalent of branch 2 if you take, just hold on, I will show you once again. So, power loss of branch 2 will be P loss 2 will be R 2 into P 3 square plus Q 3 square upon V 3 square. So, R 2 values in power unit you substitute and P 3 Q 3 you substitute, voltage V 3 just now you have computed here, this one you substitute, you will get P loss 2 will be 0.0002657 per unit. Similarly, for Q loss 2 you have to take x 2 into P 3 square plus Q 3 square upon V 3 square. So, only R x changing, this term is same, right. Once you compute this term separately, once you multiply it by R, once again multiply by x, right. So, it is also Q loss to 0.000100806 per unit. This is the loss of branch 2, because in the next iteration loss has to be added, right. Similarly, for branch 3 when J j is equal to 3, sending end node will be 3 and receiving end node M 2 will be 4. So, at that time P 4 will be P L 4, Q 4 will be Q L 4, because at 4 this is your load is there, here it is load is your P L 4 plus J Q L 4, right, this is the load same. And if you take electrical of electrical equivalent of this branch, suppose this is your branch 3 and this is your branch 4. So, here you have a load that is your P 4 plus J Q 4, right, but it is the last node. So, beyond that there is no other branches, nothing is there. So, naturally P L 4 will be equal to this one P L 4, similarly Q 4 will be equal to Q L 4, and this is for branch 3, this is the electrical equivalent of branch 3, right. So, that is why that P 4 is equal to P L 4. Here I should make it, if you want I can make it bracket also, no problem, but I told you whether it is a suffix or whether I am putting in bracket, they are same, right. So, P 4 will be 0.006 per unit and Q 4 will be 0.006 per unit. So, again from those equation A 3 A J J and D J J. So, A 3 will be P 4 R 3 plus Q 4 X 3 minus 0.5 V 3 square from the same equation of A J J. I mean this equation that is your 68, equation 68, from this equation only, right. Here you put M 2 is equal to 4, M 1 is equal to 3, right, same equation 68. So, it is your, then put all this value P 4 R 3 Q 4 X 3 and V 3 square, this V 3 you have computed, just now you have computed, right. So, that is you have computed V 3 is equal to 0.966271, just in the previous slide you have computed. So, put everything here, all these things, everything here. So, you will get A 3 is equal to minus 0.452972. Similarly, from equation your, this is from equation 69, right, from equation 69 expression of D J J, here you put J J is equal to 3, M 2 is equal to 4, M 1 is equal to 3. So, that means in this equation D 3 will get S square 3 minus R square 3 plus X square 3 into P square 4 plus Q square 4 to the power half. Put all this value. So, just now we have computed, this is A 3 we have computed. So, it is minus 0.452972 square minus R 3 square plus X 3 square I have computed here. So, 3.84124, right, into that P 4 square plus Q 4 square. So, 0.006 square plus 0.004 square whole to the power half. So, it is coming actually 0.452. Every time I told you this and this, they are very close in magnitude, but this is only here is a minus sign, right. Therefore, from that voltage equation that V j j is equal to your D j j minus A j j, that will be your equation your 66, this equation, right. So, here you put it all these two values 0.45275 minus in bracket minus 0.452972 to the power half. So, minus minus it will be plus, right. So, you simplify. So, it will be 0.95169 per unit. So, this is the value your voltage magnitude in the first iteration. Now, power loss in branch 3 in similar way, power loss in branch 3 will be R 3 into P square 4 plus Q square 4 upon V your magnitude V 4 square. So, R 3 is 1.8099 then P4 Q4 you substitute here, the square divided by voltage is 0.95169 its square. So, branch 3 power loss is coming 0.000010391 per unit. Similarly, for Q loss for branch 3 it will be x 3 into P square 4 plus Q square 4 upon V 4 square, right. Substitute again, only here this term here it is same, only here it is R, here it is x, right. If you simplify it will be Q loss branch 3 is equal to 0.40 43173 per unit, right. So, this is your branch 3 power loss. Now, next is iteration 2. I am not showing that convergence criteria difference of power losses, because only 2 iterations are shown. So, just what will be there, right. Now, iteration 2 P2 will be total load PL2 plus PL3 plus PL4, but in front of this node, I mean beyond this node only 2 branches are there, branch 2 and branch 3, right. This is branch 1, this is branch 1, right, and this is your branch 4 sorry branch 3, right. So, it is 1 2 3. So, beyond this node only 2 branches are there. So, P loss 2 and P loss 3. Similarly, for Q case it will be Q loss 2 and Q loss 3 right. So, that means your your just hold on, that means iteration 2 P 2 will be then P L 2 plus P L 3 plus P L 4 plus P L loss 2 plus P loss 3. So, this loss we have computed just now. So, sum it up all, it will be 0.01536918 per unit, this is the value. Similarly, Q 2 will be all the Qs, this all the QL 2, QL 3, QL 4 plus Q loss 2 plus Q loss 3, Q loss this QL 2 plus QL 3 plus QL 4 already we have computed previously 0.011, here also 0.015. This is this 3 is actually this one, and summation of this actually this one, right. So, plus Q loss 2 plus Q loss 3. So, it is coming 0.0111512 per unit, right. Similarly, again from the same equation you calculate A 1 is equal to P 2 R 1 plus Q 2 X 1 minus 0.5 V 1 square. V 1 is always 1 because it is slack bus, its voltage magnitude is 1. So, A 1 is equal to P 2, now you have got this much, Q 2 you got this much, right. So, put everything here, all these things you substitute, right, everything is here. So, you will get A 1 is equal to minus 0.485945. Similarly, again similar way you calculate D 1, right. So, you have got new value of A 1, you put it here, and R 1 square X 1 square is constant, it was there already 0.553818, and here P 2 square plus Q 2 square. So, this one square plus this one square to the power half. So, D 1 will come 0.485738, right. Therefore, that voltage equation, that VJJ equation is equal to DJJ minus AJJ to the power half, right. So, you put here D 1 value and A 1 value. So, this one minus bracket minus of this one. So, this will become actually 0.985739 per unit. This is voltage magnitude. Now, power loss in branch 1 in the second iteration. Same formula, P loss 1 R 1 into P 2 square plus Q 2 square upon V 2 square. So, R 1, then substitute new values of P 2, new values of Q 2 and new value of this voltage V 2, right. So, if you compute, then P loss 1 will be 0.0002391 per unit. Similarly, Q loss 1 also same thing, right, only x 2 value will be changing 0.3719 into the same thing, right. Sorry. So, Q loss 1 will be 0.0000138 per unit, right. So, this is loss on branch 1. Similarly, for J j is equal to 2, M 1 2, M 2 is equal to 3. Now everything is clear to you, right. Every step, all mathematical relationship, everything has been explained. So, everything is clear to you. It is because beyond node 3, including the node 3 itself, it is PL 3 plus PL 4 load, and beyond node 3 only one branch is there, P loss 3. That means, this is your what you call, this is your node 3. Beyond this only one branch is there, that is branch 4, right. So, sorry, branch 3, this is 1, branch 2, this is branch 3. So, 4 node problem actually it is, right. So, it is P loss 3. So, PL 3 plus PL 4 plus P loss 3 you have computed this one. So, P 3 will be getting this much 0.0111 then 0391. Similarly, Q 3 will be QL 3 plus QL 4 plus Q loss 3. So, this is your QL 3 plus QL 4 plus this one. So, Q3 will get 0.00804317 per unit, right. Therefore, you calculate your this thing A2 is equal to. So, the way it is your what you call put all these values in the same expression of AJJ is equal to that expression, and you compute A2 is equal to minus 0.466588. Similarly, expression for DJJ already we have seen. You put all these values. If you put all these value, R2 square plus X2 square I have given, P3 square plus Q3 square I have computed. That means this P3 square plus Q3 square I have computed here, it is this much, right. Therefore, your this thing this D2 will be minus 0.466588 square minus in your what you call it will come to, that is your R3 square plus X3 square into P3 square plus Q3 square to the power half. It comes actually 0.46616668, right. Therefore, magnitude of V3 is equal to D2 minus A22 to the power half. Therefore, V3 is equal to this much, right. So, it is coming 0.96579. Therefore, power loss in branch 2, it is R2 into this formula, it is coming 0.002698 per unit, right. Similarly, Q loss 2 will be X2 into P3 square plus Q3 square upon V3 square. Substitute all this value, you will get for 0.00010992. I did not put and showed it again, because every data is known, just you put it and see that whether results are correct or not, right. Therefore, similarly, for JJ is equal to 3, that is branch 3, M1 is equal to 3, M2 is equal to 4, same way. So, P4 is PL4 is equal to 0.066 per unit, and Q4 is equal to QL4 0.00 per unit. So, calculate A3 now for the same expression for AJJ. You get this equation and put all these values, right. Then you will get A3 is equal to minus 0.4525077. Similarly, from expression of DJJ, there you put all these things, you will get after substituting all these values, you will get D3 will be 0.4522869, right. You put all these values. That means, magnitude of V4, that expression of Vj, your what you call Vm2 is equal to Djj minus Ajj to the power half. So, 0.4522869 minus in bracket minus of 0.4525077 to the power half. So, magnitude of V4 is equal to 0.951207 per unit, right. So, loss in branch 3. So, same formula, P loss 3 into R3 into P4 square plus Q square, your Q4 square upon V4 square. Put all these things, you will get P loss 3 is equal to 0.00104017 per unit. Similarly, for Q loss 3, it is x3 into the same term here, you will get 0.004321 per unit. So, these are your what you call your P branch loss in branch 3, right. Now, so all the branch losses we have calculated. If you compute total real power loss, then it will be P loss 1 plus P loss 2 plus P loss 3. If you sum it up, it will be 0.00613027 per unit. So, if you multiply by MVA base into 1000, that is kilowatt you convert, right, that is in kilowatt you convert, right. So, a total power loss is coming 61.3027 kilowatt. Similarly, for Q loss, right, it was coming actually use Q loss 1 plus Q loss 2 plus Q loss 3, sum it up, and then you multiply by same MVA base into 1000, your MVA base is 100. So, it will become 29.113 kilowatt. So, in this case, and if you compare the result for your method 1 and method 2, that just what difference we can observe after your what you call after second iteration, right. So, in this method that your when you take your I square R loss and this thing, here when you are taking this injected power method at substation, it is coming 57.4820. I told you the difference is because solution is not completely converged, right. But if we do I square R loss here, it is coming 60.94 kilowatt, right. But in this method 2 also, it is coming actually 61.3027, but I square R method here is coming 60.94, right. Similarly, here it is 29.113 and here it is 28.94. So, and that means, and if you look at the, you just see yourself, if you see the voltage magnitude of both the methods, you will find for this example second method is converging faster than the first one, but one advantage of this second method is that throughout this computation there is no trigonometric term or complex number is involved, but in the second method that expression of angle delta, it can be also obtained using the same initial relationship, that two equations we wrote. One equation we wrote I is equal to your Vm1 minus Vm2 upon Zjj, that is your Ijj is equal to, another one equation Pm2 minus Jqm2 is equal to your V conjugate M2 into Ijj. Using those two expressions, that we can also get that your angle delta, your what you call angle expression, we can get it, but as in the distribution system voltage angle is not that important. Therefore, it because we have seen the variation of angle is very small, that is why magnitude of voltage is sufficient. So, second method will be better in terms of your what you call the first one, because if we need the voltage magnitude only, but there are many methods are available in the literature, but some advantages, some disadvantages you will find in every method. Here also for this example second method is better than first method, right, compared to, if you compare the voltage magnitude yourself after second iteration of both, then you will know, but different methods have different advantages. Sometimes we need real power and your what you call real and reactive component of the current also for some other purpose, but in this case you will get the magnitude of current, right, but delta can also be obtained, but that you have to write another equation for delta, but not obtained for the second method. So, but for this example, as far as magnitude is concerned, this is required. I mean, this is your what you call voltage magnitude and your power losses, right. If these two things are required, then second method one can move, but still it depends on the complexity of the network, that which one will be I mean efficient, right. So, those things are not to be discussed here. So, that means for load flow studies we have seen the two different methods, right, for load flow studies, method 1 and method 2. One thing we have noticed that you have not we have not done it through Newton-Raphson method, but coupled Newton-Raphson method also works equally well, right, but in that case computational efficiency may be less in coupled Newton-Raphson method, but here we are exploiting the radiality of the network, and based on that we are developing the algorithm. So, you should study well up to 4 bus or 5 bus problem, and just see how things can be solved. Now, another thing is that voltage stability of radial distribution network, right. So, voltage this is actually some feeling I will give you regarding that voltage stability, right. So, of the distribution system. So, voltage stability problem normally occur in heavily stressed system, right, when it is heavily loaded system, while the disturbance leading to voltage collapse may be initiated by a variety of causes. There are different type of causes. The underlying problem is an inherent weakness is the power system. So, in addition to the strength of transmission network and power transfer level, the principal factor contributing to voltage collapse are the generator reactive power, voltage control limits. These sometimes create problem. Load characteristics, of course, whatever load flow you have studied, we have treated the load as a constant power, but loads have different characteristics, right. So, and the characteristic of reactive power reactive compensation devices, we use different reactive power compensation devices, right, including fax devices of course, and the action of voltage control devices such as your under load tap changers, right. So, suppose voltage is going down, you have to change the tap of the transformer such that voltage can be raised to certain level, right. So, there are many factors associated that with voltage stability of the network. So, in general that voltage collapse actually is the process, right, by which the sequence of events accompanying voltage instability leads to a low unacceptable voltage profile in a significant part of the power system, right. So, part of the power system you find that your voltage, your what you call voltages are unacceptable because it is very low, right. So, it is the process by which the sequence of events accompanying voltage instability leads to a low unacceptable voltage profile in a significant part of the power system. There are many examples of voltage collapse in the world, but I did not bring that list, there are many. So, but the modern power distribution network is constantly being forced with an ever growing load demand, because load demand in power system is increasing. That means, on the distribution side, that load demand is increasing, right. So, distribution network also experience distinct change from a low to high load level every day, right. So, that is your what you call that load is increasing. So, if load increases, then naturally voltage magnitude will be low. So, voltage will gradually decrease. So, that then we will try to see something, but look, this is an iterative process. So, just I will give you some idea about the voltage collapse, right. And that means same equation, that equation 65 for method 2 only we will use here, because I will try to find out in terms of your voltage magnitude, right. So, in that case, that equation 65 can be written as V 2 to the power 4, right, plus 2 into P 2 R 1 plus Q 2 X 1 minus 0.5 V 1's magnitude V 1 square into the V 2 square plus R 1 square plus X 1 square into P 2 square plus Q 2 square is equal to 0. This rewriting equation, but this number is 74, right. This is your what you call that your method 2 load flow equation, right. So, in that case, or this equation I read your what you call this for V 2 4 this equation, right. All these equation we are take what we are doing it, that you multiply by this 2 and take minus common here in this term, you multiply this 2 and take minus common, right. So, this equation can be written as your V to the power 4 minus V 1 square minus 2 P 2 R 1 minus 2 Q 2 X 1 bracket close magnitude V 2 square plus this term R 1 square plus X 1 square into P 2 square plus Q 2 square is equal to 0. This is equation 75. Now, in general this equation can be generalized. So, instead of 2 we will put M 2, because this equation has come because of the electrical equivalent of branch 1 of the distribution network. So, instead of 2 we will make M 2, because M 1 is 1 and M 2 is 2 for branch 1. So, in generalize we will make will instead of 1 or 2 we will make this is V m 2 to the power 4 minus this already we have seen, right, for the load flow method 2. Only thing is that here we are rewriting this equation in different way, minus 2 P m 2 R j j minus 2 Q m 2 X j j bracket close into V m 2 square plus R square j j plus X square j j into P square m 2 plus Q square m 2 is equal to 0. This is equation 76, right. Now, you assume that let B j j is equal to this term V m square magnitude of course minus 2 P m 2 R j j minus 2 Q m 2 X j j, this is equation 77, and C j j is equal to this term R square j j plus X square j j into P square m 2 plus Q square m 2, this is equation 78, right. If you do so, then this equation becomes actually V m to the power 4 minus B j j V m 2 square plus C j j is equal to 0. So, from this equation you can see this equation actually has 4 roots. It is seen that receiving end voltage we have 4 solutions, and these solutions are these 4 actually this equation, suppose V m 2 to the power 4 minus B j j V m 2 square plus C j j is equal to 0. So, this is actually quadratic equation of V m 2 square. For example, if you assume x is equal to say V m 2 square, then this equation it is V m to the power 4, then this can be written as x square minus say B j j into x plus C j j, right. So, this equation actually quadratic equation of x, this equation, but x is equal to V m 2 square, that means that is equal to it is your quadratic equation of V m 2 square, right. So, this equation actually quadratic equation of V m 2 square. If you solve this equation, you will get 4 different type of roots. First root is 1 upon root 2. This not shown during the load flow studies, we have taken only the feasible solution. Here I will explain why other 3 solutions are not feasible solution, right. 1 upon root 2, please solve this quadratic equation and get all these value. I am writing directly all the solution, but you get it, it is a quadratic equation of V m 2 square, you get it, right. So, 1 by root 2 bjj minus in bracket b square jj minus 4cjj to the power half, then whole to the power half. This is one. Another solution is minus 1 upon root 2 bjj minus b square jj minus 4cjj to the power half, then whole to the power half. Another solution is minus 1 upon root 2 bjj plus bracket b square jj minus 4cjj to the power half. And another solution, fourth one, this is actually feasible solution. Whatever equation we have put it in different form, but this equation we have used for the second method of the load flow studies, right. Therefore, it is 1 upon root 2 bjj plus b square jj minus 4cjj to the power half, right. So, that means then these first three solutions actually infeasible solution. It is not, it has your what you call that only this one is the this thing feasible solution. Why? Look, now for realistic data, when you take the data and when P, Q, R, X and voltage all are expressed in per unit, that bjj is always positive, right. That means your bjj will be always your positive compared to your this one. Hold on, that bjj is this term, bjj is because this voltage bjj, why it will be positive, because this voltage V1 will be around unity, right. But this term in per unit, product of this term PM2 in per unit, RJJ also per unit, they are very small, their product is much smaller. Here also 2 QM2 XJJ in per unit, QM2 is small, XJJ is smaller, so their product is smaller. Therefore, then this value will be, it is square, Vm square, it will be around 1. I mean voltages whatever we get, that is we slack bus voltage we assume 1 and that voltage is around that 1, maybe little less than 1, 0.96, 97, 98 something like that. That means this term is always positive, this term is always positive when you are representing everything in per unit. This term will be equation 77, this term bjj is always positive, right. So, that is why I am writing is always positive, because the term 2 into, that means this term if you take 2 common, 2 into in bracket Pm2 Rjj plus Qm2 Xjj. So, 2 into M2 Rjj is very small as compared to Vm1 square, because this term is nearly 1, right. And also the term 4Cjj is very small as compared to B square Jj, because the second term, this one actually this is per unit, their square R square Jj plus X square Jj into this P square and Q square also per unit, their product is also much smaller, much smaller. So, that is why equation, it is equation 78. Therefore, that your what you call this very small, therefore, if you compare b square jj minus 4c to the power half, that is your this equation b square jj, this term b square jj minus everywhere this b square jj minus 4c everywhere it is there. So, b square jj minus 4c is approximately equal to bjj, right, because this term is very small. So, that means if this is approximately this is equal b square jj is approximately equal to bjj, because it is to the power half, b square jj minus this term is neglected. So, b square jj to the power half, so approximately bjj. So, right. So, that means if this term bjj, if this term is bjj, then your what you call this solution, this one and this one solution will be approximately 0, right, although minus sign is there infeasible, right, but still it is the first 1 and 2 it is becoming 0. Now, in the case of third term minus sign is there, so voltage magnitude cannot be negative. So, this is also discarded, only the last one fourth one is infeasible solution or what you call feasible solution, right. So, this term, that is why when you are computing two term ajj djj, one was negative, another was your what you call magnitude wise ajj djj are very close to that. Here also logic is same, right. So, this term and this term more or less, this term and this term more or less it is same, right. But anyway, so this fourth solution is the feasible solution, right. Therefore, hence the first two solutions of Vm2 are nearly equal to 0 and not feasible. That means, this solution actually this Vm2, this is the solution of this Vm2, right. This is the solution of the Vm2 receiving end voltage, right. This is the solution of Vm2. So, there should not be any confusion, right. This actually, this is also one solution, this is also another solution, these all are Vm2, 4 solutions. I am writing right hand side, because left hand side there is no space, right. So, Vm2. So, only this solution fourth one is the feasible solution, right. So, in the third solution I told you it is negative. So, not feasible, and the force solution of Vm2 is positive and feasible, right. So, this is actually your what you call that solution of equation 17. Therefore, the solution of 79 is unique. That means, this whatever solution we got, that equation 79, there is unique solution, because it has only one solution. This equation has the one feasible solution, the solution is unique, right. Therefore, this actually I have put it in this version, but only this version I have used for the second method of the load flow studies. So, this is equation 80. Thank you.